So today, the unit circle, I feel like the title of this section is a little misleading, because although we are going to talk about the unit circle, we are not today going to like fill in the entire unit circle with like all the coordinates like you might be used to seeing, where you have the x and the y coordinate being the cosine and the sine value. That's not what we're doing today. And if it's up to you, we probably never do that actually, because that's not how I like to think about evaluating sine and cosine for different angles. But that's not to say it's a bad way of doing it. It's just not the way I like to do it. So we'll definitely talk about that in the next class. But I'm going to try and show you what I think of as kind of the most efficient way of finding sine and cosine and the other trig functions of angles that are larger than 90 degrees or larger than pi over 2 radians. But let's remind ourselves of what we did last time just a little bit. So last class, we used special triangles to be able to work out trig values for the angles pi over 3, pi over 4, and pi over 6. This is a reminder, right? Pi over 3 is not enough room to write that there, really. Pi over 3 is 60 degrees. It's kind of maybe done. Pi over 4. Wow, all my pens. Time to cycle into new ones. Pi over 4 is 45 degrees. And pi over 6 is 30 degrees. So just as a reminder, how we evaluate sine, cosine, tangent. If we want to find cosine of pi over 3 without a calculator, I would use this special triangle. This is the 30, 60, 90 triangle, or the much more words, pi over 6, pi over 3, pi over 2 triangle. We never say that, right? You say 30, 60, 90. But I like to write it with the radian measures. And then as a reminder, the opposite side of the smallest angle is the smallest side. So 1 is the smallest side. 2 is the largest side. It's opposite the largest angle. And the square root of 3 is the medium length side. It's opposite the medium measure angle. If you want to find cosine, well, it's good to remember our acronym, SOHCAHTOA. I remember when someone first said this to me, I'm like, what are you talking about? That sounds like gibberish. And it kind of is, but it's easy enough to remember. So for finding cosine, it's the adjacent over the hypotenuse. So we look at the angle pi over 3. The adjacent is 1, the hypotenuse is 2. So our value is 1/2. And it is going to be important that you kind of develop a sense of sine and cosine and tangent specifically of those 3 angles, pi over 3, pi over 4, and pi over 6. It's going to be wanting something, you're not going to have to look it up or plot a calculator, because it's just going to come up frequently enough that you want it to kind of be in your brain, in your memory. So, and the reason that is because when we try and find sine, cosine, tangent of other angles, we're going to use those 3 reference angles. So, and that's actually kind of an important word, which we'll explore more right now. So here's our lovely unit circle, so called because it has a radius of 1. So when someone says the unit circle, they literally mean a circle centered at the origin with a radius of 1, because 1 is the unit. So this point here, although it's not super important, that point would be the point 1, 0. And that point there would be the point 0, 1. I'm not going to fill those in because that's not what we're talking about today, but I just want you to know this circle has a radius of 1. What I really care about right now is talking about these angles. So in the first quadrant, here's pi over 6, or 30 degrees. Pi over, oh, I should actually back up a minute. When we measure angles, we measure them from the positive x-axis, so to the right, counterclockwise. So here's my x-axis, here's my y-axis, and the positive x-axis is where we have a 0 degree or a 0 radian angle. And if you go counterclockwise, you're measuring positive angles. If you go clockwise, you can measure negative angles. So if you want to say like what's negative 30 degrees, it would be down this way. If I wanted positive 60 degrees, it would be up this way. So counterclockwise, it's up. I would wish they kind of did the opposite way just for the words, but positive is counterclockwise and negative degrees is clockwise. So we've got kind of these things labeled out here. Here's pi over 6, or 30 degrees, pi over 4, or 45 degrees, and pi over 3, or 60 degrees, and pi over 2, or 90 degrees. And what we're going to observe here is that the rest of the angles on the unit circle that we care about, there's lots of angles, right? But there's some specific ones we are interested in. they all have something to do with these first three angles in the first quadrant. Specifically, this angle 2 pi over 3 is pi over 3 away from that x-axis. In fact, I'm going to think of this angle 2 pi over 3 as pi minus pi over 3. If you go pi and you go back pi over 3, you get 2 pi over 3. Let's think about the math there for a second. A whole pi minus a third of a pi should give you 2/3 of a pi. Seems reasonable. I know we're getting close to Thanksgiving. Time to talk about pi. Same deal here. This angle 3 pi over 4 is pi over 4 away from the x-axis. This angle is equal to pi minus pi over 4. Let's introduce some colors. Actually, let me write one more thing before I introduce the colors. And this angle 5 pi over 6 is exactly pi over 6 away from the x-axis over here. It's equal to pi minus pi over 6. Here's what I want you to see. When we're talking about these angles, it's the x-axis that matters. The y-axis, we could care less. What I mean by that is we are always measuring angles to the x-axis, if that makes sense. Usually to the positive, although sometimes this x-axis over here is important. Here's the angle pi over 6. And this angle 5 pi over 6 has the same what we call reference angle. That if you measure that angle to the nearest x, or if you measure from that angle to the nearest x-axis, that's the angle we're talking about. So this angle here is pi over 6, just like this angle is over here. And this angle here is the same as that angle there. It's pi over 4. And a different color, it's a purple. Never use the purple pen. This angle here is the same as this angle here. And that's pi over 3. So the angle 2 pi over 3 has a reference angle of pi over 3. Because when you measure to the closest x-axis, that's the angle you get. And the angle 3 pi over 4 has a reference angle of pi over 4. And the angle 5 pi over 6 has a reference angle of pi over 6. And after we fill in the rest of this, we're going to make a really nice observation about these reference angles. It's going to be like, oh, this is super easy to find the reference angle once we see the thing. Well, let's fill in the rest of this. So let me ask you all, if I go a little bit this way, what's the reference angle of this angle I haven't even written yet? It's pi over 6, right? I went pi over 6 away from the x-axis. Well, this angle is pi. I'm adding on pi over 6, so I'm getting 7 pi over 6, which is pi plus pi over 6. And this next important angle, I'm doing pi plus pi over 4, which is 4 pi over 4 plus 1 pi over 4, which is 5 pi over 4. And this third angle is going to be pi plus pi over 3, which is going to be 4 pi over 3. So now we have 3 new angles, and each angle in the third quadrant over here has a reference angle that's one of the angles in the first quadrant. 7 pi over 6 has a reference angle of pi over 6. 5 pi over 4 has a reference angle of pi over 4. And 4 pi over 3 has a reference angle of pi over 3. And lastly, in quadrant 4, so here's the thing. I don't want to think of this angle here as pi plus something, because we always want to measure to the nearest x-axis. And in the quadrant 4 over here, the nearest x-axis is right here. So I'm going to think of this angle not as pi plus something, but as 2 pi minus the purple reference angle. So that's going to be 2 pi minus pi over 3. 2 pi is 6 pi over 3. That's 6 pi over 3 minus pi over 3. That's going to be 5 pi over 3. And this next one is going to be 2 pi minus the green reference angle, which is pi over 4. And 2 pi minus pi over 4 is going to be, write it down. It's going to be 8 pi over 4 minus 1 pi over 4, which is 7 pi over 4. And finally, the last one here in red, there's my pi over 6 reference angle, and this is going to be 2 pi. I went all the way around to 2 pi, but then back pi over 6. And that's going to be 11 pi over 6. So here is the unit circle with all of kind of the important angles filled in. We have pi over 6, pi over 4, pi over 3, pi over 2. I could read the rest of them, but I think you're all also going to look at them. Here's what I want you to see. Here is the nice observation that you want to be aware of. If I say that my angle is one of these angles, let's say I picked 7 pi over 6. You don't even have to think about it to know what the reference angle is. Drop the coefficient of pi on top. Or in other words, your reference angle is always pi over the denominator. I should clarify, for these special angles, this always works. For other angles, it does not. And I'll show you some examples in just a second. But for these, 1, 2, 3, for these 12 angles, that are not the ones that are on the axes, for these 12 angles, if I say the angle is 11 pi over 6, the reference angle is pi over 6. I just think about the pi over the denominator. If I say the angle is 5 pi over 4, ignore the 5, the reference angle is pi over 4. So you can always think about the reference angle for these angles being just pi over whatever the denominator always is, which makes it easy, or at least not terrible. Let's talk a little bit more about reference angles, which we actually don't, there's not a page in the notes for this, but I want to say a little bit more just because I feel like this section leaves out reference angles just a little bit. So let's talk about reference angles a little further. Use the back of the page to take notes. So here's what you want to know about reference angles. Here's what I want you to know about reference angles. First of all, you probably like to see what I'm writing. Okay, so a few things to know. A reference angle is always positive. So that means it can't actually equal 0. It has to be strictly greater than 0. Specifically, it's also always less than 90 degrees or pi over 2 radians. So reference angles, I could really have just said a reference angle is strictly between pi over 2 and 0 radians. Or if you prefer, between 0 degrees and 90 degrees. A reference angle is never equal to 0 degrees, or a reference angle is never equal to 90 degrees. It's always somewhere in between there. So you can always say a reference angle is acute, right? Because there's an acute angle is something that's less than 90 degrees and bigger than 0 degrees. And then the other kind of important thing is we always measure reference angles to the closest x-axis. So looking back at what we were looking at before, when I am looking at, sorry, 1 second, I'm all over the place here. When I'm looking at this angle 7 pi over 6, I'm thinking, okay, well, I'm going to measure back to the closest x-axis, and that's going to be an angle of pi over 6. So many notes. And then let's look at a couple examples. So let's say our angle, and we'll do some in degrees too. Let's say our angle was theta equal to 140 degrees. What's the reference angle? Well, I'm trying to find the angle that's less than 90 degrees. That is what you get when you measure that angle to the closest x-axis. The easiest way to see this is drawing a picture. So I'm going to draw my angle. I'm starting at the positive x-axis and I'm going 140 degrees, which is maybe about right there. It doesn't have to be perfect. So there's my 140-degree angle. And how much is left to get me to the x-axis? 40 degrees, right? Because we know that half a rotation halfway around this unit circle is 180 degrees. The reference angle we can see is 40 degrees. The way you could write it out if you wanted to show more work, I guess, is that my reference angle here is going to be 180 degrees minus 140 degrees. So if your angle is in the second quadrant, you subtract it from 180 degrees to find the reference angle. Let's look at a couple more examples. Let's say we had our angle equal to 265 degrees. Show me on your fingers, what quadrant is that angle in? See a couple different answers. It's close, it's on the border, like it's very close to being in the fourth quadrant, but it's actually in the third quadrant. So the angles, if you're drawing the quadrantal angles, which are the four angles on the axes, that's 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So we're almost there, but not quite. So there's our angle, 265 degrees. And the reference angle is going to be, well, I have to get back to 180. So I'm going to do 265 minus 180. Here my reference angle would be 265 degrees minus 180 degrees, which is 85 degrees. No, it would not be fine to subtract from 270. That's an excellent question. And I want to be very, very clear. Whenever you talk about reference angles, it is always measured to the x-axis, never to the y. It can be confusing because pi over 4, or the reference angle pi over 4, is the same measurement to either axis, but any other angle isn't. So yeah, I want to emphasize that one more time. Always to the x-axis when you're measuring reference angles. Let's look at a couple with radians, just so we can get that in our head, and then we'll move along. I drank too much coffee this morning. I feel a little shaky. Okay, so let's say our angle was something you want to see, theta equal to 10 pi over 7. Now, I want to be exceptionally clear here. Reference angle is not pi over 7. That nice trick only works for the special angles we have seen on the unit circle. This angle is going to have a totally different reference angle. That's fine. So I'm going to draw it. What quadrant is 10 pi over 7 in? Let's ask. Is it in quadrant 1? Definitely not. Is it in quadrant 2? Well, it might help if I actually label these things. That's an angle of 0 radians. That's pi over 2 radians. That's pi radians. That's 3 pi over 2 radians. And this is also 2 pi with 4 evolution. So 10 pi over 7 is definitely more than 1 whole pi. So we're definitely more than halfway around the circle. We might, I don't know. How do we know where we're at? Well, let's guess. Let's say we guessed 4. So if we guessed 4, by the way, this guess is wrong. Just want you to know. That's okay. I want to show what happens if you make a wrong guess. So if we guessed 4, well then our reference angle would be how much more you need to get to 2 pi. So I would do 2 pi minus 10 pi over 7. All right, so I need some common denominators here. That's going to be 14 pi over 7 minus 10 pi over 7 equals 4 pi over 7. But let me ask you all, is that bigger than half a pi? Is 4 sevenths bigger than a half? It is, right? Because 4 sevenths is definitely bigger than 4 eighths. And that's bigger than a half, that's equal to a half. So this is bigger than pi over 2. It can't be a reference angle, which means we picked the wrong quadrant. That's okay. We can go back and say, well, that's not right. I'm not going to cross it. I'm just going to leave that right there. What we actually should have had is this is in the third quadrant. 10 pi over 7. And our reference angle is measured to the x-axis there. So we're going to do our angle 10 pi over 7 minus pi, which is going to be 10 pi over 7 minus 7 pi over 7, which is 3 pi over 7, which is definitely less than a half of a pi. So when you find your reference angle, it should be positive and less than 90 degrees, or positive and less than pi over 2 radians. And trying to think for a second here. No, that's if you're ever like if you don't want to go through the trouble of guessing which quadrant it's in, you could compare it to the angle 3 pi over 2. Right? Because if it's less than 3 pi over 2, it's going to be in quadrant 3, and if it's bigger than 3 pi over 2, it's going to be in quadrant 4. So what we could have done if we really wanted to say, well, how does 10 pi over 7 compare to 3 pi over 2? Well, let's get a common denominator. I'm going to multiply this by 2 over 2. So get 20 pi over 14. I'll multiply this by 7 over 7. 21 pi over 14. Oh, that's bigger. So we didn't quite get all the way to where quadrant 3 ends and quadrant 4 begins. So we're in quadrant 3. I don't think you need to do this, but if you wanted to do that, you certainly could. If we have time, we'll come back and do more examples, but we probably should talk about the rest of it. So definitely. So I will point out, right? It's definitely easier to see if the angle is in degrees, if what quadrant it's in, right? Like degrees is like, oh yeah, obviously 0, 90, 180, 270. So you could change it to degrees certainly. I would encourage you to still write your answer in radians because calculus is going to work in radians a lot of times. Not always. Really, honestly, you have to be able to go back and forth between the two. People are going to use degrees, people are going to use radians, and they're going to expect you to be able to interchange them effortlessly. So that's what we're trying to practice using both. All right. So the whole point of all of this is to then be able to evaluate trigonometric functions of angles that are not in the first quadrant. Keeping things in order. So since we know all the trig values for pi over 3, pi over 4, and pi over 6, or at least we learned them last class, and the expectation is that we do know them, so definitely practice them. We can use these to help us find trig values for angles that are multiples of pi over 3, pi over 4, and pi over 6. So let's use this to find sine of 5 pi over 3 and cosine of 5 pi over 3. And there's going to be some steps. The first one is identify the quadrant. Identify what quadrant the angle, you could say the angle lives in, or you could say the quadrant the angle terminates in if you want to be more mathy with your language. So 5 pi over 3 ends in quadrant 4. And the nice thing about our special angles is, well, pi over 3 is in quadrant 1, 2 pi over 3 is in quadrant 2, 3 pi over 3 is pi, 4 pi over 3 is in quadrant 3, and 5 pi over 3 is in quadrant 4. You can kind of think out what it's going to be. And there's actually another pattern, but I don't want to inundate you with too many things right now. So let's draw this. Here's our angle approximately. And it looks okay. So our reference angle is what? You guys should all be able to tell me right there in the angle. So we're measuring the 2 pi. And it's going to be how much is that angle right there? Pi over 3, 60 degrees. Yeah. And we know it's pi over 3 because 5 pi over 3 is one of our nice angles on the unit circle that if you want the reference angle, you can just ignore the top part of the fraction. You say, oh, 5 pi over 3 is the reference angle, ignore the 5, it's pi over 3. Now, here's what we're going to do. We're going to draw the triangle. So for my angle pi over 3, the opposite side is the medium side, which is square root of 3. The adjacent side is the small side, which is 1. Well, I should say the side opposite the smallest angle is 1. And the hypotenuse is 2. Now there's a little trick here. I went 1 over, but I didn't go root 3 up. I went root 3 down. So really, although this is not my favorite way of doing it, it kind of explains how it works. That's a negative root 3. So if you go in the positive x direction, this part's going to be positive. But if you go in the negative x direction, that part will be negative. Same for the y's. The hypotenuse is always going to be positive. All right, so if I want to, sorry, I was writing down my steps, I forgot. Find the reference angle. And then we're going to find the values using the special triangle for the angle, for the reference angle. Or because you've done it long enough that you're like, okay, I know for pi over 3, sine is this value, and cosine is that value. So here's what I'm going to point out. Sine of pi over 3, pi over 3 would normally be opposite over hypotenuse, which would be normally root 3 over 2. Sine of pi over 3 is definitely the square root of 3 over 2. And cosine of pi over 3 is definitely 1/2. But now, for my new angle, 5 pi over 3, here's what's going to happen. Sine of 5 pi over 3, which has this triangle that lives in the fourth quadrant here, that's going to be the opposite over the hypotenuse, which is going to be negative root 3 over 2. And cosine of 5 pi over 3 is going to be the adjacent over hypotenuse, which is going to be positive 1 over 2. So I don't want you to have to draw this triangle every time, and you don't have to draw this triangle every time. But this is kind of the thought process about why sometimes things are negative, sometimes things are positive.
Why is the 2 for cosine 5 pi over 3 positive and not negative?
So that's a really good question. It's because we're thinking of this 2 as kind of the distance from the origin. And so we're always imagining that as a positive distance because you're just kind of going radially outwards. Whereas the legs are the x and the y coordinates. So if you've gotten in the positive x direction, positive, and the negative, negative, and so on. But yeah, it's a question that doesn't have a really, really excellent answer, but it's kind of what we're going with.
Okay. Could you explain why the root of 3?
Yes, so because we have this distance here, we are measuring downward. So you could call this point, I've gone over 1 and down root 3. Now here's the nice thing. We're going to do this a different way. Because there's a really easy way to do this without having to draw the triangle. But the point I want to make here is that sine of pi over 3 and sine of 5 pi over 3 have pretty close to the same value. The only difference is whether it's positive or negative. And so the thing that we're trying to kind of get to here is that the reason we care about reference angles is because when you have sine of an angle and sine of the reference angle, their values are the same, but they might differ by a SIGN sign. I hate that sine and sine, but it sounds the same, but like, so sine of 5 pi over 3, sine of pi over 3 have the same value, they're just different, one's positive, one's negative. And that's true for all the trig functions. If you're finding a trig function of an angle, you can find the trig function of the reference angle and then adjust whether it needs to be positive or negative. So here's how we're going to do that. There's a mnemonic device for this, or mnemonic device, there's a saying in the first quadrant, in the second quadrant, in the third quadrant, in the fourth quadrant. We like to say that, I imagine some of you have heard this before, all students take calculus. Meaning, in the first quadrant, all trig functions are positive. Sine is positive. Cosine is positive. Tangent is positive. In the second quadrant, sine is positive. Cosine and tangent are both negative. In the third quadrant, tangent is positive and the other two are negative. So sine is negative, cosine is negative, tangent is positive. And in the fourth quadrant, cosine is positive and the other two are negative. So if you know what quadrant an angle is in, you know whether sine, cosine, and tangent and their reciprocals are going to be positive or negative. Okay.
I just tried this right now, but I don't know if it's like mathematically like correct.
It's all right.
So I just did, okay, so we know that pi would be 60 degrees.
Correct.
So I just did 60 times 5, which is like 300, and then the sine of 300 is that.
Yeah. Sure. That's yes. But so yeah, you can totally change your angle to degrees if you want to, and then do sine of 300 degrees. But you still want to be able to do it all like without using any other device. Yeah. So then I suppose the last part of the instructions here are find the sine of your trig function, SIGN of your trig function based on the quadrant. So let's look at another example. So we want to find sine of 7 pi over 6, cosine of 7 pi over 6, and tangent of 7 pi over 6 without a calculator. What quadrant are we in? Well, are we bigger than pi or less than pi? A little bigger than pi, but not a lot bigger, right? We're probably in quadrant 3 because we're just a little bigger than pi, and pi is halfway around. Quadrant 3. And we can draw the, so here's my kind of usual process. Here's my triangle, and my reference angle is what? Thank you, yes. Or 30 degrees if you want to think about it in degrees. And we know for that triangle, the opposite side is 1. Well, I should say the opposite of that angle is 1. The hypotenuse is always the largest side, and the other side is square root of 2. Now, you will notice I didn't write any negative signs. So I actually don't really want to think about that. We could, right? You could totally, if you wanted to, write a negative sign there and a negative sign there, because we've gone in the negative x direction and the negative y direction. But what I'm saying is you can kind of ignore whether it's positive or negative in this step and just figure out what the signs are going to be based on what quadrant your angle is in. So here's what I'm going to point out. We know that sine of just pi over 6 would be 1 over 2. Cosine of pi over 6 would be the square root of 3 over 2, right, adjacent or hypotenuse. And tangent of pi over 6 would be the opposite over the adjacent, which would be 1 over root 3. Now, those aren't the angles we've been asked to find, but I want to use this information to then say, okay, well, if I know that sine of pi over 6 is 1/2, then sine of 7 pi over 6, well, what quadrant are we in? We're in the quadrant where which of the trig function is positive? Tangent is positive, the other two are negative. So sine of 7 pi over 6 is going to be negative 1/2. Cosine of pi over 6, cosine of 7 pi over 6 is going to be negative root 3 over 2. And tangent of 7 pi over 6, well, tangent is the one that gets to be positive. tangent 7 pi over 6 is going to be positive 1 over root 3. You don't need to actually think about these negative signs here because you can just be like, I know which one's going to be positive, which one's going to be negative. You can also use the signs here if you want. You can say, okay, well, my angle is 7 pi over 6, and sine is going to be negative 1 over 2, and cosine is going to be negative root 3 over 2, and tangent is going to be negative 1 over negative root 3, which is positive 1 over root 3. But in the name of efficiency, we are trying to do this with doing the least amount. I know I'm doing like all the work you can do, but I'm trying to show you that you have options, and you can do this doing not too much work. Let's look at this next example. Unless I should ask, yeah, question, bro.
Would we have to like get the root out of the?
I was like, yes, you should write, we should write that as root 3 over 3. Good point. Sometimes we get a little lazy if we're, yeah, good call. Other questions? Yeah. Sorry, I thought you raised your hand.
Oh,
No, you're good.
Is it in correlation with the negative and positive being that like the quadrant, the y, let's say 2 to the y is positive? The x-axis?
Exactly what Christian is saying. The reason that we have sine being positive up here is because sine is the opposite, which is going to be always the y part of the triangle. And in this first and second quadrant, that part's going to be positive. Exactly. And similarly, the reason cosine is positive over here in the fourth quadrant is because cosine uses the x part of the triangle because that's the adjacent side. And so we're going to have a positive cosine value over there. Yeah, I feel like what you said deserves more attention. So if our angle is over here and we draw a triangle, oh yeah, that's positive y and that's positive x. And if we're in the second quadrant, that's an x that's negative and a y that's positive. And right, sine is the opposite over hypotenuse, so that's why sine is going to be positive over here. Cosine is the adjacent over the hypotenuse, that's why cosine is going to be negative there. And tangent is the opposite over adjacent, that's why tangent is also going to be negative there. Over here in the third quadrant, the x is negative and the y is negative. So now sine is going to be opposite of hypotenuse, which is going to be negative. Cosine is going to be adjacent of hypotenuse, which is going to be negative. And tangent is going to be opposite over adjacent, which is going to be negative over negative, which is positive. And then lastly, over here, in the fourth quadrant, this part's negative, this side's positive. So sine's going to be negative because it's opposite of hypotenuse. Cosine is going to be positive because it's adjacent over hypotenuse. So that's why, yeah, that's a really good observation, right? That's why we're getting these signs the way they are because of how the triangles look in each of the four quadrants. You don't have to remember all that, obviously. All you have to remember is all students take calculus. Or if you want a less G-rated version of it, you can come see me in office hours. So, all right. If I want to find secant of 3 pi over 4, I'm going to think about the quadrant. That's in quadrant, not 1, quadrant 2. And the reference angle is the lovely right. Okay. I'm really not going to draw the triangle. That's not the way I like to go about doing this. What I really think you want to do is say, well, I'm going to think about well, actually, I don't even remember. So secant is never what's in my brain. Secant, I just could not remember for the life of me. I'm going to think about cosine. And then a secant is the reciprocal of cosine. And what's cosine of pi over 4? Well, cosine, or pi over 4 is the angle where cosine and sine are the same. Which is what? and tangent is 1. So let's draw the triangle. I said I wasn't gonna draw the triangle, I lied. That's where we have a 1 and a 1, and what's the hypotenuse? Yeah, exactly. So what's cosine of pi over 4? It's 1 over root 2. Okay, so now let me ask you all. If cosine of pi over 4 is 1 over root 2, and 3 pi over 4 is in quadrant 2, what's cosine of 3 pi over 4 going to be? Exactly. I'm going to write negative 1 over root 2, but yeah, you could also write it as negative root 2 over 2. I'm not rationalizing it because I know I'm going to flip it over in a second, so I don't want to bother doing extra work. But yeah, if you were doing cosine, you would write it as negative root 2 over 2. All right, secant is the reciprocal of cosine. So secant of 3 pi over 4 is going to be negative root 2 over 1, which we should just write as negative root 2. This is how I would encourage you to evaluate trig functions of the special angles on the unit circle. Find the reference, find the quadrant, find the reference angle, find whatever the trig function is of the reference angle, and then adjust the sign. Let's do another one. Let's say I wanted to find sine. Let me make sure I don't do one I already did. Yeah. Let's do sine of 11 pi over 6 and cosine of 11 pi over 6. 11 pi over 6, pretty close to 2 pi. Right, we're almost at 2 pi. We're probably in which quadrant? We're definitely in quadrant 4. So quadrant 4. You don't really need to draw it, actually. In fact, I'm going to do this one without drawing. And there's no actual reason to draw it other than to see what quadrants are in, and also to help you visualize the reference angle. But we can hopefully see that the reference angle is pi over what?
6.
Definitely. Right. Again, that nice trick only works for the special angles. If my angle was like 7 pi over 9, the reference angle would be 2 pi over 9, because that's how much more you need to get to pi. But for these nice special angles, it always works out very nicely. All right, I know that sine of pi over 6 is, so this is why we need to know what sine and cosine are of the nice reference angles, because they come up so much, right? The idea is that we have memorized sine of pi over 6, and it's going to be 1/2. We can also draw the triangle. Pi over 6, and the opposite side is 1, hypotenuse is 2, adjacent is 3. So sine of pi over 6, yeah.
How can you tell which triangle you use? The last one, it was the one that's 1, 1, or 2.
Right. So it depends on the angle. So this triangle is the 30, 60, 90 triangle. So if my angle is pi over 6 or pi over 3, but if it's pi over 4, then you use the 1, 1, root 2. And so I always like to think about how pi over 4, they're the same, right? So if you have a 1 and a 1, that means sine and cosine are going to be the same because the opposite and the adjacent side are both the same value. Cosine of pi over 6 is root 3 over 2. Now, here's what you shouldn't do. You shouldn't just say, well, I know sine's going to be negative, so put a negative sign there. Because then you're saying sine of pi over 6 is negative 1/2, which isn't true. We need to actually go ahead and rewrite. So sine of 11 pi over 6 is equal to negative 1/2. And cosine of 11 pi over 6 is equal to, you don't have to write positive, but I like writing positive to emphasize that I know what quadrant things are in. Cosine 11 pi over 6 is positive root 3 over 2. We got a little ahead of ourselves with the sine stuff. So since we only have 5 minutes left, I'm gonna fill this out later for when I play with this. But we talked about how right? He says he'll fill it out later as he still is about to do it anyway. All positive over here in quadrant 1. Sine is positive. In quadrant 2. Tangent is positive. In quadrant 3. And cosine is positive. In quadrant 4. The only thing I want to say about that is if something is positive or negative, its reciprocal retains the sign. And when you take the reciprocal of a number, it doesn't change what sign it is. The reciprocal of 2 is positive 1/2. The reciprocal of -3 is negative 1/3. So when you're finding cosecant of an angle, if sine is positive, cosecant is positive. If sine is negative, cosecant is negative. What if they don't give us an angle? We only have some information, like sine of theta is -3/5 and tangent of theta is positive. So if we're given this information, we can immediately discern what quadrant our angle lives in. If sine is negative, we're definitely not in what quadrant? 2, or what else? Not in 1 either. If tangent's positive, which quadrant could we be in? 3 or 1, but 1's out, so it's got to be 3. So we're in quadrant 3, and now I can draw something. Okay, well, in quadrant 3, sine is -3/5, so sine is opposite over hypotenuse, so it's going to be a -3/5. And what's the other side going to be? This is like everyone's favorite triangle. Not favorite, but like it's the nicest right triangle that has integer sides. It's exactly 4. Although you might say it's -4 because we've gone to the left. I probably wouldn't, but I will here. So if I want to find cosine of theta, I would say, well, cosine theta is going to be the adjacent of hypotenuse, which is -4/5. Or if I hadn't actually drawn the triangle there, if I said, well, okay, sine is opposite over hypotenuse, and I'm going to find this other side, x squared plus -3 squared equals 5 squared, x squared equals 25 minus 9, x is 4. And if I wasn't paying attention to the sign, I would say, well, I know cosine theta is adjacent over hypotenuse, which is 4/5. But then I would use the fact that the angle is in quadrant 3 to inform me that, oh, cosine has to be negative because we're in quadrant 3 where cosine is negative.
How did you go from like -4/5 to like the pi version of the angle? Like, you know, how we, most of our angles before, they were like pi over something.
Right. So what I want to point out is 4/5 is not the angle. We don't know the angle actually. So, right, we're being told, and so this is something actually I want to make super extra clear. It's really important that you recognize the difference between the angle and the trig function of that angle. Right? Sine of pi over 3 is equal to 1/2. I've seen too many times in the past where a student might have written like sine of pi over 3 equals 60 degrees because they're saying that pi over 3 and 60 degrees are the same angle. It's not that pi over 3 isn't 60, it's that sine of pi over 3 is equal to sine of 60 degrees, which is then √3/2. So we're always trying to find this ratio of opposite over hypotenuse for sine or adjacent over hypotenuse for cosine. So here they're telling me sine of, I don't know what this angle is, but they're telling me whatever that angle is, sine of it is equal to the -3/5, which is the opposite of hypotenuse. And they're asking me not to find the angle, but to find cosine of that angle. I know it's 10:50. Let me throw one more example at you because it will only take a minute. So we got another one here. Cosine is -5/6. Cosine of theta is -5/6. And although I could draw it on here, I want to show you how I would actually do it. So there's my angle. Cosine of theta is -5/6, which is adjacent over hypotenuse. I honestly usually ignore the negative sign. Although if you want, you can have it. I'm gonna find this other side here. Let's call it y. So -5 squared, if you like, plus y squared equals 6 squared. 25 plus y squared equals 36. Y squared equals 11. So y is the square root of 11. It could be positive, it could be negative. I don't actually need to know. Okay, so now, looking back at the given information, sorry, I know this does not, let me zoom out a little bit. Looking back at the given information, cosine's negative. What quadrants could we be in if cosine's negative? Thank you, yeah. So not in quadrant 1, not in quadrant 4. Tangent's positive. So what are we left with? Gotta be quadrant 3. Okay, now we're being asked to find sine of this angle that's in quadrant 3, where which one's positive in quadrant 3? Right, definitely not sine. So we know that since our angle is in quadrant 3, sine has to be negative. I'm going to use this triangle and say, okay, well, sine of theta would be opposite over hypotenuse, which is square root of 11 over 6. But we just said the angle is in quadrant 3, so sine of that angle must be negative. Sorry, you can't see that. There we go.